Before we move to the next slide, let's look at this question, the bottom question. Can we represent any 2 pi periodic function in a trigonometric series? This question is very big, important question in math history. It took a long time to find the answer of this question. It's a hard question in math history. All right. Here, I can give you the answer here. All right. We need to look at this function, f. All right. If this function is a continuous function, if this function is continuous, then the answer is yes. Okay? So it's a simple answer. So if we have a continuous function, then we can calculate this, trigonometric series. Later we will call it Fourier series. Because we will, use the integral to calculate the Fourier coefficients. Okay? And we can show the Fourier series is convergent. Because after you calculate the Fourier series, if it's not convergent, then you get garbage, right? So you have to show your Fourier series is convergent at any point of this function. It's convergent. And convergent to the function value. If the function is continuous, then it can be proved. If it's continuous, it can be proved. So the problem occurs at the discontinuities of the function. If the function is discontinuous at certain points, so at those discontinuity points, then the answer is different. The Fourier series also convergent, but the value convergent to a value like this. So let me draw a figure of this function. Later we will see that. Okay, all right. Suppose that function is discontinuous at one discontinuity point. Okay, the function is like this, discontinuous. So here you see a discontinuity point. All right. Now you can still calculate the Fourier series of this function. Okay, and this Fourier series is convergent to a point. So what point? The average of these 2 points. 1/2 of. Okay, all right. So convergent to 1/2 of f of x minus 0 plus. Let's say x0. x0 plus 0. Okay? 1/2 of it. Minus 0, take the limit from the left. Plus 0, you take the limit from the right. The two limits are different. Okay? Then the average is the value of the series, convergent series. All right? And this result, it took dozens of years finally to get this result. At the beginning, people couldn't figure out. All right. So let's look at the Euler formula for Fourier coefficients. Suppose f of x is a given function of period 2 pi such that it can be represented by this trigonometric series. All right. Then, now we apply, remember the orthogonality property. Yeah. So we can calculate all the coefficients in this way. How can you see it? Yeah. Actually, it's very easy to see it. All right. Because we know the inner product, right? The orthogonality. Yeah. Yeah. All right. Let's look at the A0 coefficient. Yeah. All right. Yeah. Suppose we have this. Yeah. So at the beginning, people, mathematicians in history, yeah, they just try to represent f function, any periodic, 2 pi periodic functions in this trigonometric series. Yeah. All right, convergent or not, they don't know. They don't know if the Fourier series is convergent to this function or not, or convergent to a different function. They don't know at the beginning. Yeah. All right. Then, suppose it is true. Yeah. It is true. Then, can you do inner product? All right. So let's do inner product. 1 with f. What would happen? 1 with f. What would happen? Okay. All right. 1, then you do inner product A0, 1, 1, right? Plus A0, sorry, yeah, I mean the summation, right? Yeah. Summation n equals 1, A n, 1 with cosine nx. And if I put it together, I can put together. Yeah. Bn, 1 with sine nx. Okay, all right. Based on the orthogonality, all gone, right? All 0. The inner product, all 0. Orthogonality. Okay, then only this left. This 1 and 1 inner product, that's just from negative pi to pi, 1 times 1 dx. Okay? That's 2 pi. So you get 2 pi times A0 equals inner product between 1 and f. So negative pi, pi. 1 times f function, that's f of x dx. Then you do division by 2 pi, you get A0. Okay? For other an, you do the similar things. For this an, you use cosine of nx to do inner product with f. Okay? Yeah, because everything is gone. Yeah, you only have an times cosine nx inner product with cosine nx inner product. Okay, you get this. Okay, then you can find inner product between cosine of nx and nx, right? Yeah. So then do division, you get it. You get pi. Okay? The inner product, yeah, here it looks like it equals pi. So you can calculate. Equals pi. You do division by pi, you get this. Yeah, because the integral is inner product between f and cosine nx. Okay? Similarly, you can get a v. Yeah? So here you can see. Yeah. So that inner product concept is very useful. Yeah. Here you use this property orthogonality property. Yeah, you can find these coefficients easily. Okay, all right. Yeah. But the next question, yeah. How do you know? Yeah. Although you can do this, yeah, because this is formulas, calculations, formulas. After you put these A coefficients back, how do you know f function equals exactly the values of the convergent values of the trigonometric series at the right-hand side? How do you know that? Okay? The question is, because the logic is like this. When you do the series expansion like this, do you get everything? Do you pick up everything? That, because there is a possibility something could be missed. Something could be missed. Although you can do it. But you only pick up part of the information. You do not pick up all the information. Okay? How do you know you pick up all the information? You pick up a partial information, not all information. Yeah. So that's a big question. Yeah. So, but how do you know you pick up all the information? So that's another property. Remember our trigonometric system. The trigonometric system, 1 cosine x sine x cosine 2x sine x. The system. There is another important property needed. Completeness property. Completeness. The system must be complete. What's the meaning? That means this system pick up all the information of the f function. No missing. No missing part. Pick up all the information. It's complete. Yeah. But the question, how do you show it's complete? How do you see it is complete? Yeah. Later we will see. Yeah. Later we will derive an inequality. Yeah. So we can pick up all the information from f function. Oh, yeah. So in physics, there is a concept called energy concept. So the f function there is a energy can be defined in this function. We use integral. Okay. Integral from a to b, and the square. We take square of this. Yeah. So this integral, we use this energy concept. Okay. Yeah. Yeah. So all the data, useful data, is included in this integral. Okay. All right. Then, so we can show this trigonometric series, the Fourier series expansion of this f function, pick up all the energies of this function. No missing. Yeah. Pick up all the energies. Okay? Yeah. So later we have the identity, special identity, possible identity. So we will see. No missing. So the system is complete. Yeah. All right. Assume triple series is convergent. Yeah. Yeah. Later. Yeah. So let's do some calculation here. Yeah. Now, our f function. What is our f function? Our f function is a periodic rectangular wave. Yeah. We know rectangular wave. We use single wave before, right? Single rectangular wave before. But here, periodic rectangular wave. Yeah. So it's not a single wave. Find Fourier coefficients of the periodic function f function. F function is given. So this is a, rectangular wave, periodic rectangular wave. Yeah. So the shape is like this. So one period from negative pi to pi wave. Okay. Yeah. So the negative half, positive half. Yeah. So it's a wave, up and down. Yeah. It's a wave, rectangular wave. Yeah. Yeah. All right. And we do periodic extension. Two sides, we do periodic extension. All right. Now, the calculation, just calculate the integrals. Yeah. So integral f function. Yeah. So you can, yeah. So 0. All right. Then, so, all right. So A0 is 0. Yeah. Then, yeah, A0, yeah. And the AN, yeah, 0. And the BN, non-zero. Bn non-zero. You cannot, all the coefficients 0, then it's a 0 function, right? Yeah. So Bn non-zero. Now you can write this f function. Yeah. So B with R, you can see B coefficients. Yeah, because you plug in. So cosine of n pi. So then B coefficients with all the subscripts are non-zero. So B coefficient with even subscripts also 0. Even subscripts. Yeah. 0 to 2. Oh, yeah, 2. 0 already in that A0. So non-zero. Yeah. 2, 4, yeah. Even. Yeah. 1 minus 1, yeah. 0. All right. So we can write expression f of x equals. Yeah. You only have the sign terms. Yeah. Why it makes sense? Yeah, here actually. Why? Let me explain why the series expansion in this form makes sense. All right. Let's look at the single wave function here. Single wave function here. Yeah. Let's look at this part. We only need to look at one period. One period. What a special function it is. Can you see? Is there any special property for this part? How special? Look at the symmetry. What kind of symmetry this function has? What is symmetry? Right? Yeah. It is symmetric with respect to origin, right? Origin, okay? Symmetric with respect to origin, like this, origin. So the point here, it's symmetric point there, yeah, origin, okay? And this function we call odd function, right? Even function, odd function. Is this even function? It's odd function. What is odd function? Odd function has the property f of x equals f of negative. Equals negative, sorry. Yeah. So odd function has the f equals negative f of negative x. Okay? Yeah, that's odd function. What is even function? Even function. F of x equals f of negative x. That's even function. Yeah. F function equals negative times f of negative. Yeah, that's odd function. Okay, all right. So the original function is an odd function. Then we do the series expansion. You can see. All right. All the even terms are gone. All the odd terms are left. Yeah, because A0 corresponds to basis function 1, right? Yeah. A0, that's the coefficient 1. Function 1, is that even function? Yeah. Function 1, yeah, because function 1, if you draw from negative pi to pi, function 1, like this is function 1. It equals 1. It's symmetric about y-axis, right? It's even function, okay? Yeah. F of negative x equals f of x. It's symmetric about y-axis, all right? Yeah. So the coefficients corresponds to the even functions, all equal to 0. Yeah. So the coefficients, cosine of nx, cosine of x is an even function? It is, because cosine of negative nx equals cosine nx. Negative. So that's even function. Even function, its corresponding coefficient equals 0. Okay? Sine x is odd, right? Cosine x is even. So all the coefficients for the even basis functions are 0. All the coefficients for odd basis functions, yeah, not all 0. Yeah, we cannot say all non-zero because there are some of them are 0. Yeah, but there must be other non-zero functions, right? Yeah, some of them 0. Yeah. But yeah, so now it makes sense. Yeah. Yeah. All right. Yeah, but we want to look at another aspect. Question: does it make sense to use a sequence of continuous function to approximate a discontinuous function? Yeah, another interesting question. Yeah, because after people get the result like this, here, the first time people see the result like this, yeah, people want to understand if it makes sense everywhere. Everywhere. Yeah. All right. So here, one thing people feel strange. One thing people feel strange. All right. First, we know this f function is not continuous function, right? There is a discontinuity. Okay? At the point 0, it is a discontinuity. Yeah. So this function, left-hand side, yeah, you can see the left-hand side is a discontinuous function, at least at certain points. Okay? All right. But the right-hand side, all these sine functions are continuous functions, right? Yeah. Then you take summation, series of continuous functions. Does it make sense? Discontinuous, continuous, how can you make them equal? Right? Yeah? Yeah. 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 Actually, you will see. Yeah. It's possible. Yeah. Why? Because this is an infinite series, right? Infinite series. Yeah. Infinite series may converge to the discontinuous function. Yeah? All right. Yeah. So here, why people at the beginning, people couldn't understand. Yeah, many people do not feel it makes sense. Yeah. That comes from our old experience. So what's our old experience? It was because we consider the truncated version of this infinite series. Let's calculate the summation of the finite terms, 4k pi, yeah, sine x. Yeah. So we truncate. Yeah. Let's say 2n plus 1 sine 2n plus 1 x. Then we stop. Okay? Yeah. Yeah. Then we can increase the terms, right? Number of terms. Yeah. Yeah. But when we consider the truncated version, always continuous function, right? It is always continuous function. Yeah. We keep going, we keep adding more and more terms, it always continuous functions. How can you, at the end, you get something discontinuous? Yeah. All right. So that's at the beginning people don't understand. Yeah. But later you will see. Yeah. Infinite series. When you look at the convergence problem at the discontinuity point, yeah, the behavior could change. The behavior could change. Oh, all right. So let's look at that part. The limit function. Yeah. Yeah. So not necessary continuous function. Yeah. So, but we want to use a graph to see it. Yeah. Graphs of partial sums. Yeah. So we call it partial sum. Okay? We take part of the terms. Yeah. The terms with index I. Yeah. All right. Yeah. Yeah. So here, yeah. Let's take partial sum. Yeah, partial sum. S1, S2, S3. Let's draw a graph to see if it makes sense. Yeah. All right. S1, yeah, only one term in the partial sum, yeah, of graph. Then S2, two terms. See? Yeah. All right. Yeah. Approximation. Better approximation. S3, three terms. Better approximation. Can you see the trend? You compare with our f function, can you see when we add more and more terms, the shape is closer and closer to the f function? Yeah? Yeah. Right? And this part, you know, the slope becomes sharper and sharper, right? At the end, the convergence point, the point, infinite series, the convergent point, convergent to this point, this value. The average, yeah, because from this side, it's a negative k, right? From that side, it's k, and you take average, it's 0. Okay? The convergent point is 0. Yeah. It's also fair, right? Yeah, it's fair. Yeah. Only the point right in the middle, it is fair. Huh? Yeah. Not closer to the upper part or lower part. It's right in the middle. Yeah, it's fair. Right? Yeah. Okay. So it makes sense. So if you draw graphs, you will see. Yeah. Yeah. It's no problem. Yeah. All right. Now, let's understand discontinuity. All right. Assume this, it is here. We have a sequence, S sequence, S1, S2 sequence. Assume it is convergent. Yeah. But convergent, you need to. So in calculus, we have theorems. Yeah. You know, we can check if a given series, a given sequence. Here it's a sequence. If a given sequence converges or not. Yeah. All right. Yeah. Here, yeah. Yeah. F0 F pi, F0 F pi equals 0. Yeah. So here. All right. Yeah. So here I explained the discontinuity. Yeah. F1 minus 0. Yeah. So you calculate the limit of that function from the left-hand side. Yeah. Left and the right-hand limits. Yeah. Minus 0. Plus 0, you calculate the limit from the right-hand side. Yeah. All right. So there, at the discontinuity point, x equals x0. So this is x0 point. Yeah. Then the S sequence is convergent at the average of f of x0 minus 1 plus x0 plus 1, 0. Yeah. So that can be proved. Yeah. So that can be proved. Okay? All right. Now you can understand, yeah, at the discontinuity, yeah, you can still apply this series expansion, but when you plug in the values, yeah, when you plug in the value, you need to know if it's a discontinuity point, then you need to use this one. Okay? Yeah. All right. So here, how do we use this result? Yeah. Here, let me explain. How do we use this result? All right. Yeah. Now it's very easy. Okay. Yeah. For example, in this series, how do we want to use it? For example, we want to look at the value at the pi. It's a discontinuity, right? Yeah. Discontinuity, yeah. So from the left-hand limit is k, right-hand limit is negative k, average is 0, yeah. Average is 0. That means the left-hand side, f of pi, you should use the 0 value for the f of pi. Then the right-hand side, you plug in. X equals pi, you plug in. Okay, all right. Yeah. Then take summation. Take summation. You get an identity. So you will get identity. Yeah. So that's correct. Yeah. All right. Yeah, actually, we can do it. Yeah. Yeah. F of pi over 2, it's a continuous point, right? Yeah. It's a continuous point, so you can plug in directly, yeah, because f of pi equals k. Yeah, continuous point, then you don't need to use that. Okay? Yeah, you just plug in the value, yeah, so you can get this identity. After simplification, you get this. Pi over 4 equals this alternative series. Yeah. Minus plus. Okay? Yeah? That series. Yeah. It's correct. Yeah. People can use other different ways to do the verification. Yeah. Here, we just use our Fourier series expansion. We can prove in this way. Okay? Yeah. It's non-trivial, right? Yeah. Here you get this result. Here. But think about if you use a non-Fourier series expansion method, it's not easy to see it, right? Yeah. Yeah. Mathematicians, they use other different ways. Yeah. Yeah. Euler also proved this result, but use different ways. Yeah. All right. Yeah. All right. Yeah. Let me see how much time. Okay. Yeah. Probably I can do one slide. Yeah. Fourier series for periodic functions with arbitrary period. Yeah. Not 2 pi period. Yeah. If we can only do 2 pi period, then too limited. So we want to extend it to arbitrary period. Yeah. It's very easy. We can do the extension. So from period 2 pi to any period, p equals 2L. Yeah. Yeah. 2L. So not L, because there is a positive L half and a negative L half. Yeah. Symmetric. Yeah. 2, so we can consider the symmetric function. Yeah. All right. Yeah. Change the period by scaling the variable. Yeah. So we just stretch, right? Yeah. So we can scale the interval. Yeah. All right. The period is 2 pi. Yeah. How to define another periodic function with the same value and a different period? Yeah. So now we want to do some transformation. Yeah. All right. Yeah. So let's scale our variable. Make x equals x times v. Yeah. S is the scale number. V another variable. Yeah. Scale number s, we can make adjustment. Yeah. Yeah. So we can make it larger, smaller, the scale number. V, a different variable. Okay? All right. Yeah. All right. So now we do variable substitution. Replace x, substitute x by sv. Yeah. Then we can factor that s out. Yeah. So v variable plus 2L over s. Now the period becomes 2L over s, right? 2L over s. Yeah. Now we want to make this 2L over s as our old period, 2 pi. How about that? Right? Yeah. Yeah. So make 2L over s equals 2 pi. Then s equals L over pi. So when we choose the scale s equals L over pi, we get a new periodic function with the period 2 pi. Yeah. So we have a formula for 2 pi. So we apply the formula for 2 pi periodic functions. Then we can get for 2L periodic functions. All right, yeah. So f of x equals, this time the scale, L over pi times v. Yeah, so we can write a, 2 pi periodic series expansion. Yeah, all right. So the formula, we can apply the old formulas. Yeah, old formulas. Yeah, yeah. All right, yeah. So here just some, calculation details. Yeah. So then you can see we can easily get a version for the arbitrary L periodic function formula, original. Yeah. Because at the end, we want to get back to the integral for the original function. Yeah. So okay, yeah. So here we do, we can go back from v variable to x variable. Yeah. All right. Yeah. Similarly, for other formulas, we do the same, change. Yeah. So we can get the version for the general L version formula. Yeah. 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 So in this way, yeah. So any periodic functions, we can calculate their Fourier series expansion. Yeah. All right. Yeah. And we know we have the convergent result. Yeah. So convergent value, which value the series converges to. Yeah. All right. Oh, yeah. So now we write the final formula. Yeah, final version formula. Okay. Yeah. Yeah. So that's pretty straightforward. Yeah. Yeah. All right. All right. Yeah. So this part, not very hard. Okay, yeah. All right. So then we need to study properties. Yeah. So now we can calculate the Fourier series of f function. Yeah. But next we need to study the properties. Yeah. So here, yeah, let's look at even odd function. Yeah. Even odd function. Yeah. So it's also pretty straightforward. So let's do one slide, then we finish this class. Yeah. Because for even function, yeah, I already explained, yeah, so you know, so that's the definition of the even function. Yeah. Even function, yeah, because the function is symmetric, then how can we see? Yeah. So this function is double, because remember, the meaning of the integral is the area below the curve, right? That's the integral. Then the negative half, because it's symmetric, it should have the same area, right? So then you only need to calculate the positive half. Negative half you do not need to calculate, you just double it. Double the area of the positive half. Yeah, because symmetric, same area. Yeah. So that property, yeah. All right. Odd function, yeah, the shape is like this. Okay? Yeah. All right. So the function, yeah. All right. Then its integral equals 0 this time. Now, so you know, for any odd function, if you take integral that is symmetric about the origin, yeah, y integral 0. We still we use area to see why this integral equals 0. And when we calculate, we allow negative area. Yeah. If the function below the x-axis, then we treat the area as a negative number. All right? So here the positive area and the negative area, they have the same absolute value but different signs. When you add them up, cancel out. Okay? Positive area, negative area with the same absolute value. Yeah. So they both cancel out. Yeah. That's why the integral is 0. Yeah. So with this property, yeah, so we can simplify our general version formula. This is our general version formula. Yeah. But sometimes we may apply the Fourier series expansion on even function sometimes odd function sometimes. Yeah. So we can simplify the expression. Yeah. All right. So this is the L version, general version. Now, for the even odd function, we have simpler versions. Yeah. Fourier cosine series. Yeah. So here, let's consider, under the condition f even, then the sine terms all gone. Yeah, because all the function part, yeah, because here function odd, all the function part all gone. Okay? Yeah. If it's an even function, okay? It's an even function, you use this property, all the b coefficients here all gone. Okay? Yeah. Can you see that? Yeah, let me explain. Here. Why the b coefficients all gone? Look at here. Why b coefficients here all gone? All right. Because f even function, right? Because our assumption f even function. Okay? Sine function, odd function, right? Even function times odd function, the whole thing is odd function, right? Whole thing is the odd function, integral from negative L to L. Whole thing odd function, this tells us must be 0. Okay? Right? Yeah. So you can see that. All right. Let me explain another one. So then we can complete another half. Fourier sine series, this time we assume f is an odd function. Then we only keep the sine terms. Yeah. All cosine all gone. Yeah. Why? Yeah. Now, f odd function, the A0 by this is 0, right? A0 equals 0. All the function here. Then an all 0 because all the function, cosine function, even function, right? All the times even still odd, right? All the function integral from negative L to L, it must be 0. So all an also 0. So only bn could be non-zero. Yeah, because all the function, the product of all the function, it's even function. Even function may not be 0, right? Yeah. So we need to keep. Yeah. So So bn. Yeah. All right. Yeah. So that's the simplification. Yeah. All right. Yeah. So let's stop here. Yeah. So next time we will study some deeper properties.